Greetings, fellow nerds. Quick question. How do you measure the solid density of a powder? Not the bulk density that includes all the gaps between the grains, but the density of just the solid as if it were one large crystal. I'll be showing that in this video where we go back to the chemistry equivalent of burger flipping, analytical chemistry. I'm sure all of you are absolutely overjoyed with enthusiasm for today's topic, measuring density. If boredom and tedium is a torture in hell, then welcome to my personal circle. I have a special personal hatred of this topic because I had to measure 500 samples in 1 hour one time. Anyway, this video is going to be more lecture than entertainment, so turn off now if you're not a chemist, or if you're a computational chemist. So density is simply the mass per unit volume of a given substance and is usually expressed in the units of grams per milliliter. It's a simple but useful analytical tool because we can get information from a sample non-destructively. Unlike, say, titration, where the whole point is to completely react away the sample. For something as simple as measuring acid concentration, it's way simpler and faster to use density. And it's broadly applicable because everything physical has a density, and occasionally non-physical things like human minds, which can be exceptionally dense. First, the basics. The easiest and most straightforward way to measure density of a liquid is using a graduate cylinder. First, we weigh the empty cylinder to get its mass and then add our liquid. We then weigh again and take the difference, which gives us the mass of just the liquid. And then divide by the volume, which we can conveniently read directly off the cylinder. And that's the calculated density. I used deionized water, so the density should be near 0.998 at this temperature. As we can see, we're a whole percent off. This is because graduate cylinders aren't highly accurate as analytical devices, so they tend to have volume errors like this. Part of the error is from the cylinder being calibrated to 27 Celsius as it says right here on the scale. My lab is a little colder. You can recalibrate to some extent by dividing the mass of the deionized water by the known density at the ambient temperature to find the corrected volume for that temperature, and then using this corrected volume for subsequent measurements. I'll be honest though, I don't bother trying to calibrate my graduate cylinders as it takes too much time for not much improvement. There's also the issue that because of the wide neck, the surface tension and reading errors on the meniscus make for unavoidable errors that cannot be calibrated out. Nonetheless, almost every chemist has a graduate cylinder, so for measuring density of a liquid, this is the bare minimum. With the basics out of the way, we can now go on to some more specialized equipment and techniques. The most well-known of these tools is the hydrometer. It just consists of a floater that's weighed down on one end with these metal ball bearings to keep it floating upright. The red wax keeps the ball bearings in place, and up here is a scale sealed inside. You can see here multiple scales have been printed on it, and since the biggest use of domestic hydrometers is for monitoring home brewing, these scales are for alcoholic beverages. As chemists, we are mostly interested in the scale for grams per milliliter. These are very inexpensive and easy to get. I got mine off eBay and Amazon for about $10. Using one of these is very easy. All you do is carefully let it sink into the fluid you're measuring, and it helps to use a graduate cylinder to hold it. Make sure the container is deeper than the length of the hydrometer, and don't drop it in or it will smash into the bottom and break. Anyway, it's designed to float, and the scale is calibrated to indicate the density where it meets the fluid surface where we read it off. Here, the fluid has a density of about 1.006 grams per milliliter. And that's it. These are tremendously convenient in that they very quickly give you density measurements in just seconds, and you don't need to run calculations. You can just read the density right off the scale. I use these all the time, especially when I'm making potassium chlorate in electrolytic chlorate cell. I can monitor the density of the electrolyte and add in more potassium chlorate salt when it's low. I can put the hydrometer directly in the cell and not have to take samples out, which is tedious and inconvenient. The problem is that most common ones don't have much range and usually only measure between 1 and 1.2 grams per milliliter, many even less. Meanwhile, common liquid chemicals like acids have much higher densities, and organic chemicals like isopropyl alcohol have densities less than that of water. Hydrometers with wider ranges do exist, but they are hard to find. So you have to fall back to the graduate cylinder method from earlier. Also, the cheap domestic ones tend to be poor quality. The scale is just a rolled up sheet of paper and can slip, destroying the accuracy. I have a couple where the paper actually fell out and landed in the bulb. So these are good for quick and crude measurements, but for high quality analytical work, we're going to need something better. And these are picnometers. They are specialized tools for measuring density, but they're just fancy flasks with fancy stoppers. The only thing special about them is that the stopper has a tiny hole bored all along the shaft. This lets air bubbles and excess liquid escape. The whole point of the picnometer is just to be a super precise volumetric flask to give you a highly reproducible volume of liquid every time. That's all. Because the neck is so narrow, the air between samples is orders of magnitude smaller than a graduated cylinder, and we can easily get 4 or 5 significant figures of precision. In fact, for most amateurs, the analytical balance you use will be the limiting factor. Before we can use it to measure our sample, we first need to calibrate it. This volume printed on the flask is completely wrong. Even professional units need to be double-checked for accuracy. To calibrate it, we're going to measure the volume ourselves using the mass of a liquid of known density. We first weigh the picnometer, including the stopper completely dry and empty. Then we fill it all the way to the top with deionized water, and then insert the stopper and let the excess ooze out of the sides and the hole. The excess is dabbed off. If it's properly filled, the stopper will be completely solid with liquid. At this point, this picnometer now has an extremely precise and reproducible quantity of liquid. Then we measure the mass of the filled picnometer and subtract from it the mass of the empty picnometer. This gives us the mass of the deionized water inside. We also note the laboratory temperature and find the density of the deionized water for that temperature. Then we use that density and divide from the mass to give us the exact volume of the picnometer. In a professional calibration, we would first put the picnometer in a temperature-controlled bath for half an hour to precisely set the temperature before stoppering it. For amateur work, though, we don't need nearly that kind of accuracy, and consulting a density table is fine. Now that we know the exact volume for this temperature, we've calibrated and can now measure the density of an unknown liquid. We just empty and fill the picnometer with it, dab off the excess, and measure the mass. We subtract the empty mass to find the liquid mass, and then divide it by the volume we found earlier. And that is the density of our unknown liquid at this temperature. This is actually sodium chloride solution of unknown concentration. But now that I know the density, I can consult a density concentration table to find it. So as you can see, despite the extra work, these are much more accurate than hydrometers and graduated cylinders. And they're not even that expensive. I got mine for just $10 each from AliExpress. But you do get what you pay for. Professional models can be hundreds of dollars, and the primary issue is how well the stopper fits. As you can see with these cheap units, the stopper is not perfectly fitting and wobbles a bit. This can give a tiny error in the volume. For amateurs, this is not a problem at all, as I found the change to be smaller than the error on my 10 mg scale, so I'm not bothered in the slightest. But for professional work with sub-milligram scales, a proper professional picnometer with tightly fitting stopper is required. If you are getting them, I recommend getting a couple of different volumes. A large volume for high accuracy when you get large amounts of sample, and a small volume when you don't have that much sample to use. For example, when I'm making nitric acid, it's far more convenient to test a small 10 milliliter sample despite the accuracy loss than a 100 milliliter sample. Now, if you're an amateur and you only occasionally do density measurements, but still want more accuracy than a graduated cylinder, then a substitute is just a regular ground glass flask with a well-fitting ground glass stopper. A plastic stopper shouldn't be used as it's a little springy and thus will introduce more errors. Anyway, with a glass stopper, you can essentially get the same results as a cheap picnometer. It's technically not as precisely reproducible as a proper picnometer, but the distribution of errors is only really visible on a professional sub-milligram analytical scale. Nonetheless, I would still get a small picnometer just because it's a nice small convenient size. If you're getting the cheap ones that are a bit wobbly but still want the best quality and reproducibility you can get, then an option is to grind down the cheap picnometer so it fits better. I'm using a silicon carbide valve grinding compound available at a car parts store. You can use just about any grinding or polishing compound just as long as it's stronger than the borosilicate glass and in the 100 grit range. Just apply the compound to the stopper and grind into the flask. Be sure to occasionally withdraw the stopper and let the compound ooze back, or even reapply the compound if necessary. As you grind, the particles get pushed out of the tighter fitting spaces and stop grinding. So you need to allow them to flow back in. Anyway, the safest way to grind is to do it by hand, but that is very tedious and took me about half an hour to get the tightness I wanted. A faster way is to use a hand drill and put the stopper in the chuck like a drill bit. Just be very careful. It's still glass and can shatter, so wear a face shield and gloves. Looking back, I should have worn thicker gloves than lab gloves, but at least you get the idea. It took about 2 minutes to grind down the stopper in the flask to a near perfect fit. Afterward, thoroughly clean the picnometer and stopper with alcohol to get rid of the compound. Now to test it, the newly ground picnometer is of much higher quality and the wobbling is nearly eliminated. I could feel an extremely tiny wobble, but I couldn't see any changes in the volume or detect any reproducibility errors. I can't say this matches the quality of a professional picnometer without extensive testing on a sub-milligram scale with error analysis, but I think this is as good as it gets for the amateur. Considering I was able to get valve grinding compound for just $5, I'd say this quality improvement was a bargain. But I'm not sure if I would officially recommend doing it for the amateur because even this wobbly unground unit had less air than a 10 mg scale. You'll get more air from your hand heating up this sample and altering the density. Nonetheless, if you're a perfectionist obsessed with maximizing analytical quality, grinding is an option. Now, a funny story and why I rationally hate these things almost as much as I hate hot plate stirrers is that one time I was tasked with measuring 500 different samples in 1 hour. That's almost one sample every 10 seconds, subtracting the empty mass and dividing the volume on my calculator. It had to be done in real time since we were monitoring the output of a chemical reactor it was running. If I had more time, I would have gotten a computer with a spreadsheet so I could input the equations, but I didn't. To save time and make it slightly easier, I created a companion weight for my picnometer. It was nothing more than a vial where I add a small amount of water so it would complement the mass of the empty picnometer. The total mass was now a simple number with only one significant figure. This number was simple enough that I could subtract in my head rather than use a calculator, and made the tedium of doing 500 samples a little easier. Granted, I still had to do the division by volume on a calculator, so I didn't win by any means, but those 10 seconds per sample felt a lot easier when I didn't have to spend 2 seconds typing in the subtraction. Anyway, I tell this story just because it's more fun than explaining what a companion weight is for. It's like a physical tare function and is useful for when you can't tare the scale. I can also segue into the final way to measure liquid density, and that's using a YouTube density meter. These are digital devices for measuring density. There are actually many different versions, and the one on the reactor broke, which is why we were scrambling to monitor it while it ran. They work by drawing the fluid into a U-tube and then vibrating it using electromagnetic coils. If you remember from physics, the mass of the U-tube and the spring stiffness of the walls make it a harmonic oscillator that resonates at a frequency that is dependent on the mass inside the tube. Because the volume of the tube is fixed and can be calibrated, by measuring the mass and running the calculation, we can measure the density of the fluid in the tube. All of this is performed in the circuitry of the density meter and it reads out in seconds. These are awesome devices, and they are also expensive so as to be completely inaccessible to the amateur. Nonetheless, I want you to know that they exist. They save so much time that if you're measuring 500 samples an hour at your job, you'll probably hold your boss hostage until they get one or replace the broken one. Not that I would know anything about that. Okay, big correction, I'm editing this in from the future, and I came across an actual domestically available YouTube density meter on Amazon. You can even see the YouTube right in the picture. So I'm wrong, you can indeed buy one as an amateur now. This seems to be advertised as assisting with the brewing of alcoholic beverages. Unfortunately for us amateur chemists, the density range is only 0.7 to 1.2 grams per milliliter. While this is great for alcoholic beverages, it's quite limited for chemistry. So I don't see a need to get one, especially at this price point. But the fact that they are available now gives me hope that a wider range of instruments will eventually become available to the amateur. Okay, so far we've been measuring liquids, but there are a few times when we want to measure a solid. The problem with a solid is that it's not always easy to measure the volume, especially if they are irregular solids. Fortunately, there are a couple of tricks. The first method is the Archimedes principle. If you submerge the solid in a liquid and rigidly hold it from sinking or floating, then the solid will experience an upward buoyant force that is equal to the weight of the liquid that it displaced. And by Newton's third law, the container of the liquid itself will experience an exactly equal downward force. The important part is that this is completely independent of the mass of the solid. It's only dependent on the volume as long as you rigidly hold it. So we can measure the volume by using a liquid of known density. So let's do that. First, we weigh the solid itself. In this case, I'm going to measure this silver round. Now to measure the volume, we need to submerge it in a liquid of known density, and I'll be using the obvious choice of deionized water. The displacement of water will tell us the volume. I'm going to hold the solid using these forceps, but the problem is the forceps themselves will displace a little water too. So to calibrate it, I dip the forceps down to the depth I think I'll be holding the silver round. And then I record the mass of the beaker of water. This is the calibration. To improve the calibration, I'm also suspending the forceps from a rigid clamp stand. This is to eliminate errors from my jittering hand. Now I hold the silver round to the same depth and record the new mass. It's important I don't touch the sides or the bottom so the mass of the silver round itself doesn't affect the weight. To record the mass, we subtract the original mass to get the difference and divide by the density of water at this temperature to get volume. Now we divide the mass of the silver round by the volume and we get our density. And that is the density of our round, which is very close to the actual density of silver. As you can see, this is a useful and simple way to characterize a monolithic solid. Interesting historical note is that Archimedes found this principle because he was tasked with finding out if a gold crown made for the king was diluted with less dense metals to steal from the king. Weighing the crown was easy, but the volume was hard to find. Archimedes could melt the crown down and reshape it into something easier to measure, but when he noticed his bath water rising when he got in, he figured he could tell the volume by displacement. Eventually, he was able to determine the gold crown was indeed mixed with silver, lowering its value. The king was pleased that he had uncovered the deception. Archimedes was pleased with his work, exclaiming Eureka when he figured out how to do it, and the goldsmith was pleased with no longer needing haircuts for the rest of his life. Now, this method is great for a monolithic solid. But what about a powder? The majority of solids we chemists work with are powders. You can't simply take the bulk volume to get bulk density, as the gaps and spaces between the grains will throw it off. And since the grains or crystals can have different sizes and shapes, there isn't an accurate correction factor we can use. So we need to somehow accurately measure the volume. We can do that with a picnometer. As usual, we first calibrate our picnometer by measuring the mass of a liquid with known density, in my case water. Since I'm using the companion weight, we can easily read off the value directly. Then we use that to find the volume. Now we need a liquid that the powder doesn't dissolve in, or at least has extremely low solubility in. I'm going to use isopropanol since I know this substance to be an ionic salt. Now we mix in some of our powder and try to dissolve some to create a saturated solution. I know very little will dissolve, but this improves the accuracy because by using a saturated solution, we turn low solubility into near zero solubility. If you're measuring something with actual zero solubility, like say the shavings of a metal alloy from your forge, you can skip this part. Now we use the picnometer and measure the density of our saturated solvent. This is what we'll use to measure our powder. Once we have that, we can start on our powder. We empty the picnometer, clean it and dry it, and then fill most of it with the powder. The more we have, the more accurate we'll be. But leave some room so we can fit the stopper later. Now we find the mass of the powder we just added. As you can see, this companion weight makes it really convenient. Anyway, once we have the mass of the powder, we take our saturated solution and add it to the picnometer with the powder. Now for the tedious part, getting all the bubbles out. Bubbles will take up space and disrupt our volume measurements, so they must be removed. It's important not to spill or lose any of the powder. We need the same amount as we weighed earlier. Once that's done, we top it up and stopper it and measure the new mass of the powder with the solvent. And now it's easy. We subtract the mass of the powder from the total mass of powder and solvent to find just the solvent mass. We divide the solvent mass by the solvent density that we measured earlier, taking into account that was saturated with powder. And this gives us the solvent volume. But since we measured the exact volume of the picnometer earlier, we can subtract the solvent volume from it, and this gives us the volume of the powder. The volume without the gaps because the solvent filled them. And from there we can divide the mass of the powder with it and that is our solid density of the powder. I'll tell you the substance, it was potassium chlorate, and the density we found matches pretty closely with the actual density. And that's how you use a picnometer to find the solid density of something like a powder. Now, a couple of questions that usually come up. Could you use a highly soluble solvent for the powder and just make it low solubility with saturation? You can, but the error will get bigger because at high solubilities, the solubility also tends to be more variable with things like temperature or ionic strength. Evaporation will also leave behind more solid and cause more errors. So it might not saturate exactly the same way as you run the measurement. For small solubilities, a 1% change is nothing, but for high solubility, a 1% change can be significant. So try and use an already low solubility solvent if you can, and lower it further with saturation rather than rely on saturation alone. I'll be honest though, for most amateur work, I've used water for even highly soluble chemicals as long as I saturate it. We amateurs just don't need that much accuracy. Second question is, can you use the Archimedes method with a powder? Yes, you can, I just find it a little messier than using a picnometer. And since you'll need a picnometer anyway to measure the density of the solvent first when you use the Archimedes method for a powder, might as well just use a picnometer all the way through. Anyway, that is how we use a picnometer to measure the density of a solid powder with liquid. As great as it is, it doesn't always work. Finding an insoluble liquid isn't always easy, and the surface tension of the liquid may prevent it from penetrating the gaps of the powder. You've probably seen this when trying to mix baking ingredients. The water doesn't penetrate the surface and seems to make a bubble. For these cases, professionals use a much more sophisticated system. Instead of a liquid, they use a gas. A gas picnometer takes a sample and puts it in a chamber. I have it shown here as an orange powder. The chamber is then completely evacuated with a vacuum pump. Once completely evacuated, a known quantity of gas is then added from a reference chamber of precisely calibrated size and pressure. After the pressures equalize between both chambers, the device then measures the pressure, and from there the volume can be calculated. Because the powder takes up space and has volume, the final pressure will be higher than if the chamber had no powder. This serves as the basis for measuring the volume of a powder. Because this uses a gas, it can even work on powders that resist analysis by liquid methods, and even measure into porous or mesoporous materials too, like activated charcoal. Unfortunately, these are also too expensive for the amateur, but they're out there. For those of you researching gas picnometers, this isn't the only configuration. Other versions instead evacuate the reference chamber or use pistons to control the gas pressure and volume. But the overall effect is the same, to measure the volume of the powder. Okay, so that was the various ways to measure density. I know it's not as cool as other parts of chemistry, but measuring density is a useful way to characterize your products. For things like monitoring chlorate cells or nitric acid concentrations, the quality of information you get out for the minimal effort you put in is extremely efficient. Thanks for watching. Special thank you to all of my supporters on Patreon for making these science videos possible with their donations and their direction. If you're not currently a patron but would like to support the continued production of science videos like this one, then check out my Patreon page here or in the video description. I really appreciate any and all support.